Dr. Mike Parsons next.
All right, can everybody hear me?
Yeah, thank you for joining us. So this talk is entitled Effects of Decomposing Fish in Prolonged Red Tide Events. And the purpose is to provide an overview of recent research to assess the effect of decomposing fish in prolonging red tide events and evaluate fish removal mitigation strategies. The project is part of a state-funded Florida Red Tide Mitigation and Technology Development Initiative. CCMP connection relates to the water quality improvement actions of reducing harmful algae blooms, same as the previous talks. With that, please take it away, Dr. Parsons.
All right, thank you very much, Corey. So first of all, I would like to acknowledge my colleagues who helped work on this project. So as Mary mentioned, I also have been working with Cindy Heil from Mote Marine. Puspa, Tim, and Shelton are other faculty members here at Florida Gulf Coast University. Puspa helped with a lot of the nutrient analyses and chemistry. Tim and Shelton are with the Lutgert School of Business, so they did the economic analyses that I will be presenting here. Next slide, please. So this was supposed to be an animation, but apparently it didn't work. But the whole idea is that when red tide blooms, basically getting over 100,000 cells per liter, it starts producing enough toxins that will kill fish. The fish then start decaying, releasing nutrients back into the water that may fuel red tide, causing it to bloom even more, intensifying the bloom, killing even more fish, so it causes a positive feedback loop. So the idea here is, well, what if we remove the fish? Would that reduce one of the nutrient sources and perhaps even reduce red tide itself? And the second part of our study was looking at, well, what do you do with the dead fish? So we looked at composting the fish as an option to mitigate the red tide blooms themselves. Next slide, please. So basically we had three major components to the study. First of all, we wanted to look at how fish were or a fish kill would be a nutrient source for red tides. So there have been studies done in the past, so we just wanted to get some more numbers under different situations and try to get a better handle on decaying fish as a nutrient source for red tide. Secondly, we conducted a cost-benefit analysis of removing fish as a mitigation tool, and if we could repurpose the dead fish as a fertilizer for local state use. Next slide, please. So I'll just be presenting a little bit of data from our fish decay experiments. So here you can see several of our graduate students basically doing decay experiments in these Tupperware bins, if you will, where we would put a single mullet into each one of these bins, about a medium-sized mullet. And we would basically just let them decay over time and measure the nutrient release in these containers over a period of a couple of weeks. So as you can imagine, these were very fun experiments for the students to participate in, but we did generate some really good data on that. We also ran these experiments in the winter time as well. So we had basically hot weather and cold weather conditions that we would look at these decay experiments. Next slide, please. So this is just looking at the results from the ammonium release rates over 14 days. 336-hour equivalent shown on the x-axis. And so you can see the micromole per gram wet weight of fish per day shown on the y-axis. That would be the release rate in micromoles, and then the duration of time on the bottom. So the idea here is it would basically be standardized per gram of fish. So if we knew how many dead fish were floating in the water and the approximate biomass of those dead fish, we could do a back of the envelope or back of the napkin calculation on what kind of release rates we would be seeing. So here we have it standardized. We looked at two different salinities, one basically representing a Gulf of Mexico value shown in blue here at 36 salinity, and also looking at an estuarine condition at 24. And you can see basically it peaks at around 4 days, which would be 96 hours, and then starts to tail off past that time here. There wasn't a big salinity difference. You can see at the 96 hour, we do see a difference by the fact that the error bars are not overlapping. But overall, we didn't see a difference in salinity. Next slide, please. Just to keep things brief, I'll just kind of give a quick result here. Our final report is available if anyone wants to look at all the nuts and bolts of this. But basically, ammonium was the major nitrogen-based inorganic nutrient produced. In fact, it actually accounted for a large fraction of the total nitrogen, especially after day 4. Ammonium release rates were up to about 50% higher than previous estimates, but phosphate release rates were less than previous estimates. So again, we're looking at mullet. Past studies would look at pinfish or mixed fish assemblages. So we may have some differences, as you may expect, depending on what fish was caught in the fish kill and would be decaying. So again, we have more numbers. These are not necessarily the end all of the numbers for these type of studies. Salinity did not appear to have much of an effect on nutrient release rates. In fact, it was statistically insignificant when you looked at it as a factor. Nutrient release rates generally stabilized within 2 to 7 days. So if you were going to be removing fish, you probably should act fairly quickly. If you document a fish kill and it's a big enough fish kill to act on, we still need to see what that number would actually be. You probably need to act on it within a week. And temperature had a clear effect. I didn't show the winter data, but nutrient release rates were about half as much. And we can actually model that in terms of how release rates would change over different temperature regimes. Next slide, please. So the next part I'm going to jump to quickly was the work that Tim Allen and Shelton Weeks did. And so they looked at economic data, and they worked with colleagues at the University of Florida with some of the reports and the results generated there as well. But what I'm just summarizing here is you can see the number of visitors versus how many there were on average based on previous years. So the lost visitors, so we lost about 50,000 each year during the red tide and blue-green algal blooms, spending per visitor estimates, and the annual lost expenditure. And you can see the average monthly cost then for Collier County, it was $3.8 million per month. And for Lee County, it was $8 million per month that was lost. Next slide. So basically just averaging this, it looks like counties were probably losing somewhere on the order of $6 million per month when red tide was present. So one thing I need to clarify on this is they would compare months when there was red tide present greater than 100,000 cells per liter versus when it was less than 100,000 cells per liter. And so they definitely saw an economic downturn in the tourism tax dollars when red tide was present greater than 100,000 cells. That also coincides basically with when red tide concentrations are high enough to be killing the fish. So counties were losing a significant amount of money when red tide was present. We also looked at numbers on how much the counties were spending to clean up the fish, either floating in the water, but primarily up on the beach. And you can see it basically was around $2,000 to $6,000 per ton. So just looking at that $6 million per month versus, up to $6,000 per ton, it looks like the numbers might work on removing fish. It looks like it could make sense, and the cost benefit analysis would support it. But the big if here is, will the removal actually reduce red tide intensity? So what we need really is to get better numbers on how many fish are out there floating in a fish kill, put in the nutrient release rate numbers that we've produced and past studies have produced to see what that nitrogen loading is, and is it worth removing that many fish. So we could do the numbers right now and kind of play with it, but that's really kind of the next step in terms of getting that hypothetical scenario and then trying to apply it and see if we can get the actual field data to back it up. Next, what do we do with the dead fish? Next slide, please. So just briefly here, what we did was we actually got fish from Clearwater and Tampa Bay, and we collected somewhere on the order of 500 or 600 pounds of dead fish. And that was really fun too. And we put them in a control tank, which was just with water. And then we also did a treatment. And so the water was just fresh water, just municipal tap water, basically. And so in the control tank, we didn't do anything else but put the dead fish in the water and put them in these big 750-gallon tanks. In the treatment tanks, we added a composting accelerant known as SBE that was developed by our collaborators with Wilco, and they specialize in livestock composting. And so using animal material and composting that. And the before here basically refers to before we would mix everything up in the tank. So we would take photos and then we would mix everything up and then we would do our sampling. What you notice in the control tank is there are no floating fish. And in the treatment tank, there are floating fish. Basically in the control tank, what happened was we had a lot of insect larvae in the tanks, and they basically consumed a lot of the dead fish material. And so you basically ended up with this kind of soup, and then you had a lot of bones sitting on the bottom of the tank. And so you can look at the treatment on the right, though. The fish stayed intact. For some reason, the larvae didn't like this treatment effect so much. And then on the far right, you can kind of see how the fish would degrade into this almost like milkshake or pudding type consistency. So it was making a product that we think could be useful as a fertilizer. You can see some seagrass blades and seaweeds in there because, again, these fish were collected off of the beach and they were not degraded nearly as quickly as the fish themselves were. We did an NPK analysis on this treatment material, and it was nitrogen rich. It was a bit depleted in phosphate and potash or potassium versus what you'd expect in a regular fertilizer. But it could be a nitrogen source to be used in a fertilizer product in the future. Next slide, please. We also measured the brevetoxin content. The only brevetoxin that was detected was brevetoxin 3, PBTX3. It was present in the control and the treatment, and in both cases, it was basically gone within 3 weeks. So the degradation composting process in general looks like it can remove the brevetoxin. So the SBE treatment didn't seem to remove the toxin any better than the control. So it just looks like the natural degradation process can remove the brevetoxin, which is good news because if we want to use this as a fertilizer, this demonstrates that it looks like composting can remove the toxin, so we wouldn't have to worry about that with the dead fish. Next slide, please. So wrapping up here, summary and next steps. Fish are a major source of ammonium as they decay in the water. So removing the fish may actually remove a major nutrient source, particularly since red tide does have an affinity for ammonium itself. Fish removal appears to be economically feasible. We just have to put the numbers together on, how many fish need to be removed to really make a difference and how much would that removal cost. So the numbers are at hand, so we can start playing with them a bit, but we'll really need the field data to back that up. Composting does create a nitrogen-rich, toxin-free product. Interestingly, could this be an organic fertilizer? Because these are natural fish, and so they're produced, or they grow out in the environment. So if we take them and compost them, could they be actually an organic fertilizer? Maybe not if we use an SBE treatment, but I don't know enough about organic fertilizer production to know that. Another interesting thing is they could be nitrogen neutral because the fish have the nitrogen, they compost, creating this nitrogen product. That nitrogen product came from the Gulf of Mexico, and ultimately maybe it would return to the Gulf of Mexico. So we're not taking atmospheric nitrogen and turning it into fertilizer like in a lot of synthetic fertilizer processes. This is just fertilizer that came from the ocean and would be going back. So there are some possibilities here. Again, that's outside of my field, but just some interesting things to think about. So again, as I mentioned twice already, the next steps are to look at the actual nutrient and red tide reductions associated with fish removal to see if this is really a feasible way to go on that. It looks promising. And examine the feasibility of large-scale fish composting and utilization as a local fertilizer fish. Because right now, a lot of these dead fish just end up at a landfill or an emergency landfill, depending on permitting. And so maybe we could repurpose it and actually make something good out of this. Last slide. And this is just my contact information if anybody has any questions or comments, and thank you very much.
Thank you, Dr. Parsons. Really interesting stuff. We do have time for a question. If anybody wants to ask Dr. Parsons a question.
I have a quick question, Corey, on the composting. Is this something that can be done locally? I don't know that much about it, but
yes,
the cost of moving fish around the landscape, it would be extremely expensive. But if it's a short run from the beach to wherever it is, then that would make it a lot more feasible.
Yeah, I guess it'd be the definition of local, but definitely within the county, where the fish were collected. A lot of small, maybe even hobbyists who do composting are really interested in this. There's an organic fertilizer program within Lee County. They are not permitted, my understanding is right now, to be able to compost animal waste. So we would need to look at permitting to be able to compost the fish. But there is a lot of interest in this, and I barely know how to compost, right? And so we would definitely be interfacing with those composters and looking at the logistics of it. Where would be the best place to do this? Because that has to be included in the costs. They are included in that removal cost. So I would imagine that $6,000 number is probably transporting the fish farther away than the $1,600 one. But yeah, the next steps here, bring in the people who actually do all this and see if we can make the numbers work and create, a good product out of this.
Yeah, and I'll just say there's very little attention given to this topic. I mean, the whole point of red tide is to kill fish and generate its own nutrients, and that's not really a part of the cycle that anyone's been looking at that I know of.
Right. Yeah. And, for me, I'm an algae guy, so here I am working with dead fish. So it's expanding my knowledge too.
Well, thank you very much, Dr. Parsons.